All right, welcome to week 5. This is going to the chapter in your textbooks, chapter 5, and this is going to be taking a look at some of the aspects of air pressure, how we measure what it is, that sort of thing. So, first of all, if we want to just generally define air pressure, it's something that exerts a force on the surface of all objects, you, the ground, all of that sort of thing. Air is a gas, so as long as it's above absolute zero, these molecules are going to be in constant motion. And as these molecules in constant motion, our atmospheric gases, collide with surface areas, that creates air pressure. Now you can read through a lot of this other stuff, but I'm going to skip on to the next page and talk about how we measure it. Now initially, we used to measure air pressure with a mercurial barometer. All right. So in other words, if you look at this illustration here, you can see that we would put an evacuated glass tube down into a pool of mercury, and the force of the atmospheric pressure would push that mercury up the evacuated column. Now, on average sea level barometric pressure, you can see in this slide here, is 29.92 inches, meaning that mercury would rise 29.92 inches up the tube. Now, in aviation, we use inches a lot in barometric pressure, but in surface maps, surface analysis, and upper air charts, we use millibars. And I'll talk a little more specifically about some of these units in a bit here. But just suffice it to say for now, the 29.92 inches of mercury is the equivalent of 1,013 millibars. So in other words, 1,013 millibars is the average surface air pressure on Earth. All right. Now there's going to be if as we increase temperature, we change the air pressure a little bit. If we add humidity, we can change the air pressure. We can change the air pressure a bit. So there can be some variations that happen with it, but more or less 29.92 inches or 1,013 millibars average surface air pressure. Two very important numbers to keep in mind. All right, now how do we measure it today? I mean, it's not very convenient to have a 30-inch or longer mercurial barometer hanging around or in the cockpit of an aircraft, because really all an altimeter is in an aircraft is a barometer. So we've gone to these. These are called aneroid barometers, and you can see here a pretty simple device. We have an evacuated chamber, all right, and it's surrounded by aluminum, and when the air pressure increases or decreases, it's going to move this pointer and give us an equivalent to inches. In the case of this barometer here, you can see it's a little over 30 inches here. So like I say, the aneroid barometers are used in aircraft, at least general aviation aircraft today, to determine how high we are above sea level. And they are very accurate. I mean, and that will tell you that the barometric pressure does decrease at a very even rate as we leave Earth's surface. I'll show you that graphic in a minute here. Just thought I'd throw this one in here too. We do, if you want to get a constant recording of barometric pressure, atmospheric barometric pressure, we use this thing here called a barograph. The applications for these are in climate stations. The Forest Service uses them a lot out in remote areas. So anyway, just thought you might want to see that, a barograph. That could actually keep the barometric pressure for about a week before you'd have to go in and change it. All right, some of the units of measure that we use here. It gets a little complicated, but let me simplify it for you. If you go down into the metric scale there, you can see that sea level pressure could be 101,325 pascals or 1,013.25 hectopascals. And that's the one you should remember, because hectopascals equal millibars. Remember what I said, that sea level pressure was 1,013 millibars. We can see here that it's also 1,013.25 hectopascals. So millibar is really a metric conversion, all right? And this will, further down, I'll tell you that 1 bar is equal to 29.53 inches. So 1,013 millibars is then about 29.92 inches. Later on, you'll see, and this will become important, the usual worldwide range of barometric pressure at the surface is going to be 970 to about 1,040 millibars. However, having said that, you can see that the absolute range has been significantly outside that occasionally, really rarely. For example, you can see the lowest surface pressure ever recorded was 870 millibars. That was Typhoon Tip. That was a tropical cyclone in the Pacific Ocean back in 1979. And then you can see the highest ever recorded barometric pressure at 1,083.8 millibars in Siberia. This was a very cold outbreak of very dense air. All right, here's a graphic on air pressure, really just to show you how air pressure decreases steadily and really fairly rapidly as we leave Earth's surface. So when we look at this, you can see across the bottom here, if you look to the extreme right at the bottom, red line is indicating the surface, that would be around 1,000 millibars. Remember, 1,013 millibars. And then as we increase in altitude, you can see by the time we get to the equivalent summit of Mount Everest, our air pressure is down to only about 300 millibars. That's up around 29,000 feet, all right? And then from the top of Everest, you can see that, boy, the air pressure decreases very rapidly. And, essentially, once we get past, you can see about 19, 20 miles above Earth's surface, you're really out of the atmosphere. 99% of the atmosphere is from that elevation down. All right. Horizontal variations in air pressure in meteorology, this is the important thing. Yes, we are concerned about vertical changes in air pressure, but more importantly, really in tracking weather systems, it's the horizontal variations in air pressure that's important. Okay, here is just, sort of an idealized schematic, this map of a surface analysis of North America, or at least part of North America, certainly all of the United States, okay? The lines you see written on this map are called isobars. And in one of the labs you've done and you've seen on maps, you're going to see these. Now, these isobars, by convention, are every 4 millibars apart. Now, what is the definition of an isobar? It's simply lines of equal barometric pressure. So that means any place one of these black lines is going through, for example, the 1012 millibar line, all the locations that line goes through will have a barometric pressure of 1012. So anyway, this is how we can track systems going across the United States. And again, keep in mind that by convention, they're separated by 4 millibars. This is really just written out what I just said. So, if you want to come back and read this, go ahead. I guess, one of the things I should just mention down near the bottom, you probably already know this by now, but high pressure systems, clockwise outward circulation, are the systems that generally bring us fair weather. Okay. Low pressure systems, these are systems that have counterclockwise and inward circulation, are going to be areas generally of cloud and precipitation. All right. Okay, now one other concept that Chapter 5 gets into I want to just touch upon here. Convection. This is when air can rise and can also fall back down. So let's take a look at this first bullet here. I've called it expansional cooling. So in other words, as we get air to rise, and there's many ways we can get air to rise. It can be from convection, that is the sun heating the ground, heating the air and causing that air to rise. Air can also be forced up mountain ranges. It's called orographic lifting. Air can be forced up fronts, cold fronts or warm fronts. That's frontal lifting. And then air can be forced to rise in the center of a low pressure system. That is convergence lifting. But anyway, just generally though, if we cause air to rise and cool, those molecules are going to get further apart. Okay, so when the air partial lifts, less air pressure, right? So these air molecules get further apart. That causes the temperature to fall. So we've got a couple of reasons why air cools as it leaves Earth's surface. Number one, it's leaving the source of heat, which for the most part is Earth's surface. But it's also, as it rises, remember, those molecules are getting further apart, and as they get further apart, temperature also drops. Okay, so the point really is, as we cause air to lift, it expands, it gets cool. All right, just the opposite happens though when air is forced down. And that can happen in high pressure systems. It can happen on the lee side of mountain ranges and for some other reasons. But point here is this: as we cause air to fall, it gets closer together, compresses, and those molecules are closer together, causes a warming. So just in summary then, when we lift air, causes the molecules to expand and cool. When we have air fall, get lower in elevation, it compresses and it warms. All right, there's an area of meteorology we call adiabatic processes, okay? In an adiabatic process, what we're really talking about here is a parcel of air rising, lifting, can also be falling. Let's talk about the rising part first. A parcel of air that rises, but no heat is exchanged outside that parcel to the surrounding air. That's what we mean by adiabatic. All right. I think the best thing I can do here is let me just show you this right here. I'm going to grab a sheet of paper for myself here. All right, so if you take a look at this, what we've got is, let's look at the left side first. What we see here is we see a small circle. It says 10C. That's 10 degrees Celsius. So this is a parcel of air that's not exchanging any heat from the surrounding air, and it's rising in the atmosphere. So you can see here, after it's risen 1,000 meters, it's dropped 10 degrees. It's dropped from 10 degrees to 0 degrees. Okay, as it rises another 1,000 feet, or 3,000 meters, sorry, 3,000 meters, it's dropped another 10 degrees down to minus 10 degrees Celsius. What this is telling us is, this is called the dry adiabatic rate. What it's telling us is that for every 1,000 meters of ascent, the temperature inside that parcel of air drops 10 degrees Celsius. Okay? So what? What does this mean? Well, it's kind of interesting, because if this parcel on the left continued to rise, it will eventually reach what we call saturation point. That relative humidity inside that's going to become 100%. Okay? Then what happens, look over to the right. We've had the dry adiabatic rate, which is approximately 10 degrees Celsius per 1,000 meters. Once it reaches saturation level, now we're seeing a lot of that water vapor that's invisible condense into liquid water. That's what the cloud is. Remember, clouds are liquid water or ice crystals, all right? So once we start seeing the conversion of water vapor, H2O water vapor, into liquid, that process releases the latent heat of condensation. So now we're adding a lot of heat to that environment. So look over on the right side there in the cloud, you'll see that the moist adiabatic rate, saturation, is less. In other words, now it's only cooling 6 degrees Celsius per 1,000 meters. And the reason for that is because of all this latent heat that's being released, caused by the phase change from H2O gas to H2O liquid. So this latent heat of condensation is a very important factor in adding heat into the atmosphere, and really can cause these clouds to continue to convect and lift and rise and get bigger, and eventually could turn into something like a cumulonimbus cloud. All right, that's going to be all right now for chapter 5, and talking to you later.